Okay, so now we're finally going to wrap up this chapter, so another long chapter. Okay, so the discovery of new chemicals has been ongoing for years and years. Of course, way back in ancient times, people knew about gold. Gold appeared in nature in its elemental form. Silver, copper, all of those elements were discovered thousands of years ago and of course used in different things. And many elements are radioactive, and so they're not stable, which means they really don't exist, that we only know about them because of technology. And then there's many elements in between that have been discovered along the way. So it was about the early 1800s where it became easier to isolate elements from their compounds, and so the known number of elements jumped from 31 to 63. So as these numbers increased, different scientists began to investigate ways to classify them because it was really hard to keep them all organized. Mendeleev was in Russia. Meyer was in Britain. They both came up about the same time. They both came up with classification schemes. And both of them, the way they classified it is by noting similar chemical and physical properties. So these things occur over and over again, and so they kind of organized them where they put all the elements that were similar in the same column. And I'm not sure if that's what Meyer did. He might have done something different, but Mendeleev put everything that was similar in the same column and was able to organize them that way, and then you could see that the patterns reoccur. So, yep, Mendeleev, he actually left blanks in the periodic table. He said elements with similar characteristics should be in the same family, and so it forced him to leave these blanks in his periodic table. For example, gallium and germanium, neither were known at the time, but he left them blank and put arsenic under nitrogen because he said arsenic acts a lot like nitrogen. So they were blank spaces. And then, of course, years later, those elements were discovered, and he pretty much described what they would look like when they were discovered, and then when they were discovered, they matched what Mendeleev had said that they should act like. So that's where his periodic table is kind of accepted as the main. So he's kind of known as the father of the periodic table. So anyway, periodic law says that when elements are arranged by atomic number, and actually let me back up for a second. Originally, there was no such thing as an atomic number because they didn't know, even at that time, they didn't know that there was such a thing as neutrons. So they actually organized things by mass. And interestingly enough, if you stare at the periodic table long enough, you actually find a few elements where the one with a higher atomic number actually weighs a little bit less than the one before it. And so there are a few little glitches, like for example cobalt and nickel. Nickel weighs just slightly less than cobalt, even though nickel has one more proton. Anyway, of course that has to do with the average neutrons. But anyway, back up to this. So periodic law says then when elements are arranged by atomic number, so it was later that's what it was discovered, their physical and chemical properties vary periodically. In other words, you kind of get to the end and then you sort of start over. So we're going to look at a few periodic properties that you can predict by looking at the periodic table. And the three that we'll be looking at are atomic radii, atomic radius, ionization energy, and electron affinity. Okay, so let's talk about atomic radii. Of course, the radii is just what you think of if you've got an atom. The radii is the distance from the center to the outermost edge, which would be the furthest out electron in our case. So within each period, as you go across horizontal row, atomic radii actually decreases with increasing atomic number. So that's actually kind of unusual, and we'll talk about why in just a minute. So as you go across the periodic table from left to right in the same row, atomic radii decreases with atomic number. Which does make more sense if you go down a column, atomic radii gets bigger. So that makes sense. As you go down, it should get bigger because you were adding more, more and more shells. So it should get bigger and bigger as you go down. But now, why does it get smaller as you go right? Here's a picture of it. So you can see, as you go down the same row, so hydrogen, lithium, sodium, potassium, they just keep getting bigger and bigger and bigger because you're adding more and more shells, so that makes sense. But if you go across the same period, you can see them getting smaller. So what's happening here? There's two factors that determine the size of the atom. So like I just got through saying, one factor is the principal quantum number. So the larger n is, the more shells that are in the atom, and so of course the size of the orbital. So that's what dictates the fact that it gets bigger as you go down. But the other factor is called the effective nuclear charge. Now, what is this? This is the positive charge an electron experiences from the nucleus. So if we're like here's our nucleus right here in the center. How much charge does it feel? And what we have to do is take into effect all the electrons that occur here in between the nucleus. So the farthest out electron and all the ones in the middle are called shielding electrons. And so in other words, how much does this feel? How many electrons are in the way? Of course, the more electrons that are in the way, the less of a pull it has, and so the larger the molecule is going to be, or the atom, sorry. And this kind of goes along with the first one, the principal quantum number. So how far out it is. But anyway, let's look the next slide. Okay, so this picture is a little bit better than the last one. Anyway, so here's our positive charge, our nucleus. Here's our electron of interest. Now, any electrons that come between the nucleus and the electron of interest are shielding electrons. So let's say that these are we're on my third row. So we've got 1, 2, 3, 4 electrons. If we're on the third row, these are the electrons from the first and second shell. And so they're the only ones that are shielding, but none of the electrons from the third shell, the same shell as the electron of interest, none of those are shielding. So, so only the ones below it. So first, one thing we can do is we can calculate an effective charge. Z effective is the effective nuclear charge. And we do that by taking the number of protons, so that's the atomic number, and we subtract any shielding electrons that come between the outermost electron and the nucleus. So all the shielding or core electrons. One thing you want to make sure and do is include any d electrons if there are any. So they get included in with the shielding electrons. So let's look at oxygen. Oxygen's in the second row. It has 8 protons, and since it's in the second row, the only shielding electrons are the first shell electrons. So that's where the 2 comes from. There's 2 electrons in the first shell. So oxygen has an effective charge of +6. Bromine has 35 protons, and it has 28 shielding electrons. So where does that come from? Well, bromine is in the 4th row. So we have to subtract the first row electrons, and there's 2 of them, the second row electrons, the S's and the P's, and then the third row electrons are the S's, P's, and D's, so that's 18. So 18 plus 10 is 28. So that's where the 28 comes from. 35 minus 28 is +7, so it has an effective charge of +7. Now, how does that, you can go back and look at the previous slide. I can't go back when I'm recording, but we can let's look at the elements in the third row. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So as we can see on the previous slide, and by our trend, we know that the radii decreases as you go to the right. So as we go to the right, the radii decreases, which at first doesn't make sense because you're thinking, whoa, we're getting bigger and bigger and bigger. We have more and more protons. Well, let's look at the effective charge. So first, let's look at how many protons they have. So sodium has 11, 12, 13, 14, up to 18, 15, 16, 17, 18. Now, how many electrons are shielding electrons? So so this is the same as, I'll do that, Z. This is Z. And now we want to subtract the shielding electrons. Well, because all of these are in the third row, we've got 2 first row electrons and 8 second row electrons. So we have a total of 10 shielding electrons. So if we subtract 10 from sodium, we have an effective charge of +1. If we subtract, again, there's only 10 between magnesium, and because the electrons in the outermost shell aren't counted. So there's 10 shielding electrons here, 10 here, 10 for silicon. So keep going, and you can see that the effective charge keeps getting bigger and bigger and bigger because the same number of shielding electrons, but there's more and more protons in the center pulling on them. So they're going to pull a little bit tighter on those outermost electrons so you're going to, the more protons there are with the same number of shielding electrons, you're going to pull more and more, and that's why the the radii get smaller and smaller as you go to the right. So that's kind of an interesting thing. So again, atomic radii.
Weather outside is right.
The atomic radii gets smaller as you go to the right, and smaller as you go up. So, or you could say larger as you go to the left and larger. So it gets larger that way. Larger as you go to the left and larger as you go down. Okay, so what about ions? So ionic radii is the measure used to describe the size of an ion. So again, same thing. You've got your nucleus and then your highest, the measure to the outermost electron. Now, ions gain or lose electrons, so the outermost electron could change. So because a cation has fewer electrons and the same number of protons as the parent atom, that means that the effective charge gets bigger because they're removed from the outer shell. So now we don't have we're kind of into a lower shell, and so the effective charge gets bigger, and so the radii gets smaller. So a cation is always smaller than the atom from which it's derived. So, you know, for example, if we had iron metal, and then if we had iron ion, it would be smaller, and probably even smaller about the same if it was Fe3+, because it is losing one of the d electrons. Anyway, so cations are always smaller than the atom they came from. So in the opposite way, an anion always has more electrons than the same number of protons, and the same number of protons as the parent chain. So in other words, the effective charge actually gets a little bit smaller, and that's because there's greater repulsion among all the electrons, so they're kind of further out. They're farther out, and so anions are always larger than the atom from which they came from. So, you know, if we have a nitrogen atom and then we have a nitrogen -3 atom, it's going to be bigger. ion, nitrogen -3 ion is going to be bigger. So here's exactly what I just said. So if we have an aluminum atom, an aluminum ion will be smaller. These values are picometers there. So picometers, that's actual distance. Pico is 10 to the minus 12. So these are very tiny. But anyway, you can see that the radii drops. Here, if you add more electrons, the radii gets a little bit bigger because they're pushing away from each other. Okay, so what if we have two species that are ionic or neutral that have the same electron configuration? That means they have the same number of electrons, and that also they're said to be isoelectronic. They have the same number of electrons. So here's some examples. Neon is 1s2, 2s2, 2p6. Sodium, which has one more electron or one more proton than neon and one more electron, but if it's lost that electron, also has the same electron configuration. Magnesium 2+, aluminum 3+, and then going the other way, fluorine negative, O -2, and -3. They all have the same electron configuration. And then the second row here, again, all have the same electron configuration. They kind of match. This is kind of why they form these ions, because they want to have that noble gas configuration. So the question is, are all of these, because they all have the same number of electrons, are they all the same size? And the answer is no. Again, it depends, it depends on the number of protons in the center and then the number of shielding electrons. Because all of these have the same, we're in the very last electron. So of course, the difference, since they all have the same number of shielding electrons, it's the number of protons that will determine its effective charge. And so the greater the nuclear charge, the smaller the radius. So that's very similar to that, to the trend going across a row, because that's the same, almost the same number of electrons. It's got the same number of shielding electrons, and it has more protons. So this is the same way, same number of shielding electrons and more protons as your charge, as your number of protons go up. So if you were looking at these all have 18 electrons. They all are isoelectronic to each other. But if you look at argon, has 18 protons and 18 electrons. Potassium has 19 protons and 18 electrons because it's lost one. Calcium has 20 protons and 18 electrons because it's lost 2. Of course, chlorine has 17 electrons and 17 protons and 18 electrons because it added 1, and 16 protons with 18 electrons because there's added 2. So since they all have the same number of electrons, which one is smallest? It's the one with the biggest atomic number. So calcium will be smaller, potassium will be bigger, argon will be bigger, and sulfur will be the biggest. Okay, ionization energy is the second trend that we're going to look at. And what is ionization energy? The amount of energy required to remove the most loosely bound electron from an atom in its ground state is called the first ionization energy. So in other words, to take away the first electron, how much energy is needed to pull that electron away. So yeah, we say that a lot of elements like to give up electrons, but you still have to kind of take it away from that element. So some are easier than others. So this would be considered the ionization energy, to take the first electron, the first ionization energy. If you want to remove a second electron, then to remove the second one would be the second ionization energy, which usually decreases. It's usually a little bit higher than the first one. Now the energy to remove the third electron then would be the third ionization energy, and so forth. So how are ionization energies, how do they vary across the periodic table? Okay, so like I said a minute ago, energy is always required to remove an electron, but and so all ionization processes are endothermic, meaning you have to put energy into them, but the values are always positive. But as the size of the radii increases, ionization decreases. So you can imagine if you've got your protons here and your electron out here, the further away it is from the nucleus, the easier it's going to be able to be stolen. So first ionization energies decrease as you go. So if you're looking at a periodic table, ionization energies increase as you go to the right and increase as you go up. So decrease as you go down or increase as you go up. So it's harder and harder to remove an electron. So if you had, much smaller atom, it'd be harder to remove this electron than it would be to remove that one. So as you go up a column, it's harder and harder to remove that electron. And as you go to the right, for the same reason that the size decreases, it's harder and harder to remove an electron as you go to the right. There are some deviations from this trend, but we won't worry about them, just the general trend. You can see here, so like I said, here's some of the deviations as it goes up and down, but you can see as you go down a column, the ionization energies go down. It makes it easier and easier. So, or as you go up a column, they get higher. It's harder. And same thing here, cesium, rubidium, potassium, sodium, lithium. It's harder and harder to remove as you go up. Again, as you go to the right, it gets harder and harder. So going from lithium to neon gets harder. From sodium to argon gets harder. From potassium to krypton. Like I said, there's a few variations, but we won't worry about that. Now, if you want to remove a second or third electron, sometimes it's not too bad and sometimes it's really hard. So let's, why would that be? Well, everything that's in the first column, the first ionization energy might not be too bad. You can see here lithium's low, beryllium, boron. This is the first row. It's getting higher and higher and higher. For the second row, to remove an electron from helium or lithium is way, way higher. But beryllium, who doesn't mind having a +2 ion, it gets it drops back down and then it gets higher. Same thing here, the third row. So boron doesn't mind having a third electron removed, but beryllium absolutely doesn't want to, and lithium doesn't want to, because lithium really only has 1 electron to give away. Beryllium has 2, boron has 3. So you can see how this sort of stair step comes along, because it's prohibitive to remove the next shell down. But if you're staying on the same shell, it's not too bad. So it's harder to remove valence electrons. It's easier to remove a valence electron from the outermost shell, but to then take more electrons from an inner shell makes it harder. And then, so we have, so we said, let's just review what we have. So here's our periodic table. We said that size increases going this way. So this is atomic radii. And then, let's do blue. So then we said that ionization energies let's say, okay, atomic radii increases in this direction. Ionization energy increases as you go. It's going to be the opposite. It's harder to remove an electron as you go up, and it's harder to remove an electron as you go to the right. So it's exactly opposite. So ionization energy increase is opposite of atomic radii increasing. And then finally, we have something called electron affinity. An electron affinity is the energy change for the process of adding an electron. How much is an atom willing to add an electron? So for some elements, energy is released when it accepts an electron, but for other elements, energy is required to accept an electron. So for a chlorine atom, then the first electron affinity is illustrated by this. So we take neon 3s2 3p5, we add 1 electron, and so actually heat is given off. 349 kilojoules per mole is given off when this electron is added. So this ion has become more stable. The more negative the electron affinity, the more stable the negative ion that is formed. So the more electron, that's the higher the electron affinity it has. So the general trend goes from lower left to upper right. So again, oops, that one's not very visible. Let's use red. So if we have electron affinity increases in the same way that ionization energy increases. So the harder it is to remove electron, the easier it is to add an electron, is kind of the same thing. So electron affinity also. So electron affinity and ionization energy both increase from bottom left to top right, and then the atomic radii increases opposite to that, from the top right to the bottom left. There are a few deviations, and that probably has to do with sort of closed subshells. So, you know, the noble gases have a completely filled shell, and so we don't want, it really doesn't want more electrons. So we kind of don't, they don't have electron affinity. So we kind of stop here at fluorine. Group 2 has a filled subshell, S subshell. So the next electron goes into the higher P subshell. So that's less, it's not as happy. They don't like to do it as much. And then the group 15 has the half-filled P subshell, and so the next one has to be paired. So there are some little blips, but overall the trend is from to get more electron affinity as you go up and you go to the right. So you can sort of see the trend that the more negative the number is, the more stable it is. So the electron affinity goes up as you go up, and it gets more electron affinity as you go to the right. But don't count the noble gases. And again, this is one of the weird exceptions right here because it's a closed subshell. So we have to go to the higher energy level. So, but then you can see it increasing again. So kind of blippy, but in general, the overall trend is to get high electron affinity increases in that direction. All right, so the last thing we're just going to do is just go through the different groups and look at some of the elements. So group 1A are called the alkali metals. They have the largest atomic radii in any row. They react violently to form hydrogen gas. They all will tend to form a +1 ion easily. They're all metals. They form with oxygen in a 2-to-1 ratio. Here's just some interesting things about, they're all very, very reactive, so they really don't exist freely in nature. They're hard to store. They're very soft metals. You can cut them with a knife oftentimes, like with a table knife. Sodium obviously is found in a wide variety of compounds, including salt, baking soda. Potassium is found a lot. You can read that as fertilizers, soaps, explosives. Lithium used extensively in batteries, which I'm sure you already realize that. The group 2A are called the alkaline earth metals. They tend to form a +2 ion fairly easily. They also react with water to form hydrogen gas. They have that closed S subshell configuration, so they're a little less reactive. They're all metals, but they still are very reactive and too reactive to exist in its elemental form. Calcium is found a lot in seashells. It's also important for your bones. Magnesium is also important in nutrition and is found in Epsom salt and milk of magnesia. Barium is often used in fireworks. I think that shouldn't have an E there, X-rays. Beryllium is also used in X-ray tubes. Strontium is especially used in fireworks. It burns a bright red color. The transition metals, there's a whole lot of transition metals, but in general, we know that transition metals can have different oxidation states, meaning they can have more than one charge. And they're all metallic and shiny and hard, dense. They're usually good conductors. They tend to react with acids. You can see some of them here. Just some examples. Titanium is very dense but very lightweight, so that's why it's often used in joint replacement and aircrafts. Copper, we know, is used in wiring and water pipes. Nickel is often used in coins, so that's the name, the nickel, because it originally had all nickel. Iron is used in lots of things, catalysts, paint, blood. You know, iron, you have to have iron in your blood. Of course, silver and gold in jewelry. Palladium is often used as a group. Through 3A, now they tend to be, we're starting to get to where we've got a mixture of metals and nonmetals in the same column. Aluminum is the most abundant metal on Earth, very strong, light, and malleable, so we know that's why it's used for foils. They tend to have a +3 oxidation state, although they can vary a little bit. Boron is found in making glassware, so like all of our glassware in the borosilicate means that it's resistant to breaking when you heat it or cool it quickly. That's because of the boron. Gallium can melt in your hand. It's used in LED lighting. Indium is used in mirrors. I think they're just showing you that it can bend easily. Group 4A is probably the most, well, no, I think it's the next one. So group 4A forms the most covalent compounds. Carbon is an extremely widespread element that's you know, in all over the earth. It's found in diamonds and graphite and coal. It's one of the most important elements for life because most molecules in your body are made with carbon, because most biological compounds contain carbon. Lead. There's lead. It's kind of not so shiny, so we're getting out of the metals. Germanium used for semiconductors. Silicon is also one of the most abundant elements on Earth. It's not a metal, so it's not the most abundant metal, but it's one of the most abundant in silicon. Silicon dioxide is quartz. It's found in many rocks and minerals. It's also used in semiconductors because it's a semi-metal. Group 5A tends to be one of the most varied states because we can have different negative charges, and they can also be positive oxidation states. So it's got a range of metals, metalloids, and nonmetals, and so you can see the metallic character increases as you go down the column. Here's phosphorus for making fireworks and matches. Nitrogen, of course, is an inert element, but found in lots of, found in amines, amino acids, anything, a lot of biological compounds. And then, of course, arsenic, used in car batteries and as a semiconductor, and also being used as a poison. Okay, groups 6A all form -2. Now we're getting to be more consistent again. So they all form -2 ions, although there are a few positive oxidation states possible. They all react vigorously with alkali and alkaline earth metals. They're all nonmetals. We know oxygen and sulfur are essential for life. Oxygen, of course, is used in breathing and is necessary for all life except for something that's anaerobic, which there's not very many of. Sulfur is used to make rubber stronger. Selenium is used in semiconductors. Well, you can read some of this. Anyway, these are all important elements. The halogens, you should know that name. So if there isn't a name for a group, you don't need to know it, but if there is a name, you should know it. So halogens, group 7A, are all, now we're getting all consistent again, they're all -1 charges. They have very high electronegativity, in other words, electron affinity. They all form diatomic gases as elements except for bromine, which is a liquid. But they're all diatomic. iodine sublimates. So bromine is the only non-metallic liquid at room temperature. Chlorine means green. We know that's what's used for keeping swimming pools clean, and it's in laundry bleach, and it's in salt. Iodine is important for thyroid function in the body. And then finally we have our noble gases. They have minimal reactivity. They're all monoatomic. They're all colorless, odorless, tasteless. They have a closed shell, so all the other atoms try to be like the noble gases, where they gain or lose electrons to try to be like them. You know, neon is this orange color, but they all glow. They're all gases that glow. And so they're often neon lights, neon in quote lights, can be different colors. Xenon is used for lighting lasers and phototubes. So that pretty much wraps up this chapter. What should you be able to do in this chapter? You should be able to convert from wavelength to frequency or frequency to wavelength, and know that, you know, how one goes up and the other goes down. Be able to calculate the energy of a photon. Determine the wavelength and frequency of any hydrogen atom transition from, you know, one energy level to another. Don't worry too much about de Broglie. De Broglie just says that if something has a wave nature, it also has a particle nature. You should understand the rules for quantum numbers, to be able to tell me the quantum numbers for different elements and what the quantum numbers mean, and what they tell you, and how to figure out what the quantum numbers are for different electrons. Be able to use Pauli's exclusion principle, which says that no two electrons can have the same 4 quantum numbers. In other words, you can only have 2 electrons in any orbital. Then you should be able to figure out the electron configuration of an atom using the Aufbau principle. Determine the configuration of an atom using the period and group numbers. So in other words, being able to write the electron configuration by using the periodic table. And you should be able to do the orbital diagram, the electron configuration, and then the noble gas configuration, which is the shortest one. Be able to apply Hund's rule, and that just says that when you're adding electrons to a subshell that has more than one orbital, they don't pair until each orbital is half filled, and then they go back and pair. You should be able to, like I said, write the noble gas configuration, write electron configurations for ions, and apply periodic trends for atoms and ions, including atomic or ionic radii, ionization energies, and electron affinity. And that is the end of this chapter.